Okay, we're back with our last two topics of the forces unit. And the first topic that we're going to talk about today is air resistance. And we're not going to get into it at the same level that you would, at the same depth that you would get into air resistance in a college calculus-based physics class. But we will talk more about it today than we ever have before. And we'll get a little bit farther into the discussion of it. So to start off, real quick, what is air resistance? It is a frictional force that resists the motion for a frictional force that resists the motion of an object moving through a fluid. A fluid being either a liquid or a gas. This can you can have now. Obviously, for air resistance, we're talking about an object moving through a gas. But air resistance can the term. I guess we could say the drag force is a little bit more general of a term. Drag force can help us calculate the motion of an object as it goes through water. Let's say an object falling through an area of water. Now, how does air resistance affect free fall? And we really shouldn't be calling it free fall if we're dealing with air resistance, because free fall, by definition, the only force acting on an object is gravity. And if we're also talking about air resistance, or the force of air resistance, this frictional force, then we're not really dealing with free fall. But in general, how does it change what would happen in free fall? I guess would be a better way to put it. Air resistance reduces the velocity of an object, because it's a frictional force, which therefore reduces the maximum height of that object, as well as the range of the object. Okay, and we won't be calculating, how much does it reduce the height, how much does it reduce the range? At least not. I don't think we will be. But we will be looking at some other things, such as looking at how air resistance does it causes objects to fall at terminal velocity instead of simply under free fall, continuing to accelerate. Okay. So let's get to a very general model of air resistance. And this is a perfect example of why we deal with models in physics. It is one of those things where it is impossible to be 100% right with air resistance. It is just too complicated. There's too many complicating factors. So instead what we come up with is a model that predicts pretty much what the right answer is going to be. As you get more and more advanced in your knowledge of physics, you can deal with better and better models. We're just going to be dealing with kind of the first basic model of air resistance. Or I guess you could say an ideal picture of air resistance. So when we want to calculate, when we want to talk about air resistance, we want to talk. We're going to view it through the lens of how big is the drag force. Okay, drag force we're going to symbolize as FD. Drag force. Drag force is the force that arises. It's pretty much the same thing as air resistance. When we talk about air resistance, we're talking about a force of friction, which we're going to call the drag force that's acting on something. The drag force, as far as we're going to use it, is equal to BV. Okay, where B is a positive constant that is known as the drag coefficient. Okay, that's going to be different for every object based on its mass, shape, what the object is moving through. You don't need to calculate any of those things. We're just going to say that there's some positive constant called the drag coefficient, and then V is the speed of the object. Now, on occasion, in more advanced classes, you might see this, or in some cases you might see this. There are actually different regimes that those equations are true. Sometimes that speed is squared, sometimes it's not, depending on the situation. Like I said, this is just a model of air resistance, okay? It's a first approximation model. Now, one of the interesting things that air resistance does, and we'll get to that when we talk about terminal velocity, is air resistance causes objects to fall for longer than they rise. Now, let's take a look at why that might be. Let's look at an object that is rising, and let's say you took an object and you threw it straight up in the air. Okay? So here is our object. We'll say object rising. The equation, let's see here, or let's put an axis on there. We'll just do an up axis, positive y. Now, what would the forces on this object be if we're not neglecting air resistance? Well, we would have a force of gravity pointing down. We would also have the drag force, the air resistance, pointing down. And therefore, our net force equation would be negative Fg minus Fd equals ma. If you were to solve for the acceleration, not only would you have to account for the force of gravity pulling the object down, you would also have to account for this drag force, okay? So initially, as soon as you throw it, you get what would be a very, very high acceleration, because this would end up being mg minus bv equals may. And as the object was just thrown, as it just starts off, v must be very high. It's moving very fast when you just throw it or launch it or whatever. So this term is very high, meaning our acceleration is much higher than normal. As the object rises, because it's going to have a negative acceleration, speed is going to decrease. And as that speed decreases, this term decreases, which means our acceleration decreases, until the object gets to the very peak when it's not moving anymore, when v is 0, the peak of its motion, and the acceleration is simply equal to g. So, the acceleration for an object that has air resistance acting on it is much higher than g, or is higher than g, for every point up until the very peak of its motion. What that means is it's going to accelerate at a greater rate. And since the acceleration and the velocity point in different directions, that means it's going to slow down at a much greater rate than it would without air resistance. So, if you remember when we talked about free fall, we said an object rises for just as long as it falls. With air resistance, we're already cutting down on the time for the object to rise, because the acceleration that is causing it to slow down is so much bigger when we account for air resistance in this case. When the object is falling, on the other hand, we still have Fg pointing down, but now that the object is falling, it's moving downwards, the drag force must be pointing up. And if we write a net force equation, we get Fd minus Fg equals ma. And we should point out that since the object is now accelerating, let's see here, since the object is now, it's going to be, yeah, it's still accelerating downward, but something interesting is going to happen. bv minus mg equals ma. Okay, so now that the object is, let's take it from just when the object starts to fall, gets to the peak and comes back down. When it's at the peak, we said that this term is 0, so the acceleration is just negative g. As the object continues to start moving down, it gains some speed, this term is going to get bigger. Okay? And if this term gets bigger, look at that. It's now a positive term minus a negative term. So initially, we just have a big negative number for the acceleration. But as this term gets bigger, the acceleration is actually going to get smaller and smaller, because while mg is going to stay the same magnitude the whole time, bv is going to be getting bigger and bigger. Since mg starts off bigger than bv, our acceleration is going to be negative, but that negative number is going to be moving closer and closer to 0 as the object picks up speed. And it turns out that when the object gets to a certain speed, it gets just fast enough, then this term balances out this term. They're exactly equal to each other, and we get no acceleration, which means the object does not gain any more speed. Okay, the v stays the same. And if v therefore stays the same, the object never has any acceleration anymore for as long as it keeps falling. And at this point, once ay reaches 0, then we have the following. bv minus mg, may is now 0. We have bv equals mg. So in other words, there's some velocity that can be reached that causes there to be no more acceleration and that speed, to remain the same for the rest of the fall. And that speed is given by the equation, I'm just dividing the b over to the other side, mg divided by b. This is known as terminal velocity. So to recap, why does it take longer for something to fall than it does to rise? Over here, there is no terminal velocity. The acceleration is always bigger than it would be in free fall, so the object slows down quicker. Over here, the acceleration is always smaller than it would be in free fall, so the object does not slow down as much per second. And as a matter of fact, there comes a point where the object stops slowing down at all, the object doesn't speed up as much, I should say, as it would under normal free fall circumstances. So there comes a point where the object actually stops speeding up at all. That's called hitting terminal velocity, and that depends on the object, the mass, the shape, the size, what sort of fluid it's traveling through, etc. But this is the example. This shows us why, when you throw something up, and air resistance cannot be neglected, it actually takes longer for the object to come back down than it does for the object to rise up, and that's a very interesting. Case. Let's see here. Is that all I want to talk about with terminal velocity? So yeah, we can calculate the terminal velocity for some object, given that we know the mass, acceleration due to gravity, and this constant b, which is made up of a whole bunch of other things. Okay, last thing I want to do is a little bit of a review. What do graphs of an object falling under air resistance look like? So we've actually done this before, but we'll just kind of refresh our memory. We're going to make 3 graphs of x versus t, v versus t, and a versus t. Okay, and okay, you guys can see that, good. So what I'm going to do is I'm going to draw a solid line is free fall, and the dotted line is with air resistance. And for all of these graphs, we're going to assume down is positive, and the object starts at origin. So we know that under free fall circumstances, for position versus time, we will have an object that increases its velocity the entire time that it's falling. And if it increases its velocity the entire time it's falling, the slope of an x versus t graph is the velocity, so we should have a slope that is increasing the entire time. That looks like this. Okay? Now, instead, for an object that has air resistance acting on it, we have a graph that looks like this. Because under air resistance, we just found that at some point, the object reaches a terminal velocity. We can tell that that's terminal velocity because the slope stops changing, the velocity stops changing. Slope stops increasing. We also would have a graph of velocity versus time. Normally, the velocity would just keep going up and up and up, but if we approach its terminal velocity, that means that the velocity should eventually not change anymore. So here would be the graph of there would be the graph in free fall. Here would be the graph of terminal velocity with air resistance. The slope approaches 0. And then finally, normally, For the acceleration in free fall, it is a constant 10 meters per second downward. With air resistance, it doesn't look like that. The acceleration decreases toward 0, which is when terminal velocity happens. And we've gone over these before, but I want to just refresh and review. Okay, so you very rarely will see air resistance in AP problems, but in the off chance that you do, or you're asked to model it or predict what would happen, this should give you a little bit of a guide as to what goes on. Okay, one more topic to talk about.